So these videos are in complement to the solutions. If you looked at the solutions and you thought you were fine with them, there's no need to watch these this video. So we're going to be doing questions 1 and 2. So here we go. We have a parallel plate capacitor. It's set up vertically. So got that here. Boom. The plates are separated by 10 centimeters, so let's just right away convert that, 0.1 meters. And the electric field has a magnitude of, so E, magnitude of 3.00 times 10 to the 4th newtons per coulomb. I don't know why the PDF moves my subscript to my superscripts to subscripts. With the right plate being positive, okay, and the left plate being negative, okay? That means that the electric field, would go in this direction. A small opening is cut into the plate and a single free electron is placed just here. Okay, so here's my negative. Okay, so that's why. This is going to repel and this is going to go and shoot out the opening here. And what we're doing is we're looking for that velocity, which I'll just call VF. The drawing is not to scale, right? An electron is not that big. So other things that I know, well, I know the charge on an electron, so that is negative 1.6 times 10 to the negative 19th coulombs. I also know the mass of an electron. That's on the first page of the reference table, 9.11 times 10 to the negative 31st kilograms. So find the electric force on this. So here we go. Magnitude of Fe is equal to Q naught. E, we'll find the magnitude and then we'll talk about what the direction is, right? So we know this E, I did do it as a magnitude, but it's to the left. So the force is going to be to the right because it's a negative particle. A negative particle's field force is opposite the field. So there we go. So 1.6 times 10 to the negative 19th coulombs times 3 times 10 to the 4th newtons per coulomb. The sig figs don't really matter here, folks. So I'm just kind of playing a little fast and loose here. 4.8 times 10 to the negative 15th newtons. And I know that that's to the right, okay? I didn't make a declaration or anything because there's no particular need yet. But you know what? We should just do that. Let's say to the right is positive. So then this would be positive, and then we will decode that to mean to the right. Might as well be consistent since we're going to be doing some kinematics here. So find the acceleration. Well, that's just straightforward F net equals ma. And so here the only force, because we said gravity is not relevant, the mass of an electron is so small that I multiply that by roughly 10. That's not going to do anything. So even though technically it does accelerate downwards, who cares? The net force on this is just the magnitude of Fe is equal to the mass of the electron A. So I've got 4.8 times 10 to the negative 15 newtons. You're like, that's such a small force. But it's that force on a really, really tiny mass, which has very little inertia. So the acceleration is actually going to be ridiculously large. But we kind of expect that. Okay, so throw all that into my calculator, and I'm getting 5.27, we'll go 3 sig figs, times 10 to the 15th meters per second. Wow, that's large. So C, find the speed of the electron when it shoots out the opening. So here, because I know that the electric field in here is constant, I know the electric force is constant, so I can use kinematics. So VF squared is equal to VI squared plus 2A delta S. So I'm told that it starts at rest, so that's going to zero out. So VF squared is equal to 2 times 5.27 times 10 to the 15th meters per second squared times 0.1 meters. Okay, square root, plus or minus. We'll pick the positive root because I said to the right is positive, and that is the direction it's going. Let's see if these are very, very large answers. 3.2 5 times 10 to the 7th. Ooh, close there, because our particle can't go faster than the speed of light. but that particle is truck in there. That's a large electric field, and it's speeding that thing up for quite some amount of distance, at least for the scale of an electron. When we use these parallel plate capacitors in order to accelerate particles, generally it's not over this large of a distance, it's over a much smaller distance, right? And the electric field is not as large, right? Because that is a huge final speed. So how long does that take? Well, VF is equal to VI plus AT, or I could use delta S is equal to VIT plus 1/2 AT squared. If I don't want to use a number, in fact, that's probably the better way to do it. Therefore, I don't have to use one of my numbers that I just got, so we can not have rounded figures. So 0.1 meters is equal to 1/2 5.27 times 10 to the 15th meters per second squared, t squared. T is equal to plus or minus, get rid of the minus because time can't be negative, and we get and the square root of that quantity. Get the very small 6.16 times 10 to the -9th seconds to traverse that distance. Okay, and so there we go. A kinematics in a capacitor problem. So now let's look at number 2. All right, we have a pith ball. Okay, so now it's macroscopic, and the mass of that pith ball is equal to 0.006 kilograms, because I'm not playing around here. I know that if I'm given the mass like this with these problems, then I'm going to probably need to find the weight. Once again, in the last problem, we didn't do that because it was a microscopic thing, not a macroscopic thing. So context really matters. 588 newtons. Okay, cool. It's unknown charge is suspended in a parallel plate capacitor. It's oriented horizontally. Boom. So there we go. Here gravity matters because the object's macroscopic. As I said, the top plate is positive. The bottom plate is negative. And we know that the magnitude of the electric field is 2,400 newtons per coulomb. What is the amount of flavor of the charge? Okay, well, if it's positive, negative, we know that the gravity force is going to act downwards. Now, this thing is suspended. That means I know absolutely that the electrostatic force has got to act upwards. Something's got to balance gravity. But if we look at this positive to negative, that means that the electric field must go to the bottom of the page. Notice here that FE is anti-parallel to E, therefore Q0 must be negative. Or I could just say like, okay, what would be attracted upwards towards a positive plate? It's going to be a negative object, but I like doing my electric field analysis. Okay, so now we just got to find that. All right, well, let's make a declaration. Up is positive. I'm going to switch back over to a normal color. And then I can do F net is equal to MA, positive FE minus FG equals A, and I know it's suspended, so the A is going to go to 0. FE is equal to Q0 E, and I know FG is already equal to 0.0588 newtons. Therefore, the magnitude of Q0 is 0.0588 newtons divided by 2,400 newtons per coulomb, and that gives us some number which I will discover when I put it into my calculator as 2.45 times 10 to the -5th coulombs, or to express that another way, I know it's negative 24.5 microcoulombs, or negative 2.45 times 10 to the -5th coulombs, and there is the answer. So with that, hopefully you can do number 3 and 4. 3, if you've looked at it, is just kind of the reverse of 1, and I'm not leading you through all the internal steps. And number 4 is a little bit trickier. That's a projectile motion problem. So the big hint there is going to be you're going to have to separate things into a chart. What's true X and what's true Y, okay? So there is your hint.